Hey guys, Mr. McKinney here, just going through the X-Wing problem in case you missed it in class today or just wanted to see part of it again. All right, so let's read through it. Yoda is lifting Luke Skywalker's X-Wing fighter out of the swamp using the Force. He is standing 30 feet away and holds his arm out in the direction of the fighter to help him concentrate. The X-Wing is rising vertically at a rate of 3 feet per second when it is 5 feet off the ground. At what rate is the angle of elevation of Yoda's arm, which is pointed towards the fighter, changing at this time? Now we're going to ignore Yoda's height. We're just going to assume that his arm is at the ground level. Technically, that's not true, but to set this problem up, that's the way we're going to look at it. So let's draw a picture first, and let's think about the overall what's happening. So we've got Yoda down here in the corner, and then over here, a distance of 30 feet away, we have the X-Wing, which is now rising, and Yoda's arm is pointing at it as it goes up. So we've created a triangle, and we've created a right triangle. So up here is the X-Wing, and it is moving up. So if we call this maybe X and Y, and then the angle down here, because it's at what rate is the angle of elevation. Angle of elevation down here, we're going to call theta. Now the 30 feet horizontal distance is a constant. So at all times, X equals 30, and at all times, dx dt is 0, because the rate of change of a constant is 0. Now Y is changing, it's a variable, but we do know the rate at which it is rising vertically. So we know dy dt, it's 3. We don't want to plug in 5 right here because that 5 is not a constant. That's at the instant when we're 5 feet off the ground. So we have to kind of draw two pictures. The overall picture of what's happening as the X-Wing is moving, and then at the instant when y equals 5, what does the picture look like? And at the instant when y equals 5, we would have a triangle with theta, 5, and 30. We're going to use this triangle later on to figure out what theta is at this instant. But we're going to use the overall picture to set up what's going on in this problem. So we're given information about the opposite side and the adjacent side. So the formula that I want to use that has an opposite and adjacent in it is going to be tangent. Tangent of theta is opposite over adjacent. So in this problem, tangent of theta is y over x. Now, we know that at this instant, y is 5 and x is 30, but we don't want to plug both of those in. You can only plug in things that are constants before you take the derivative. So I can plug in this x is 30. So I can say tangent of theta equals y over 30. I don't want to plug in the 5 before I take the derivative, or else it's not going to work. Now to make this a little bit easier to take the derivative, I'm going to rewrite this fraction as 1/30 times y. So at this point, I can now take the derivative. So the derivative of tangent is secant squared theta. And we need the derivative of theta with respect to time, because that's what this problem is asking for. At what rate is the angle of elevation changing? So the question is asking for d theta dt. Keep in mind that in calculus, you should always be using radians. So if you see a problem that's in degrees, convert the degrees to radians and then work in radians. Keep your calculator in radians and always do all your work in radians. So if you ever have an angle in degrees, convert it to radians and then do your work in radians. All right, back to where we were. Derivative of tangent is secant squared, and then the derivative of theta is d theta dt. The derivative of 1/30 y with respect to t would be 1/30 dy dt. So I'm trying to solve for d theta dt. I need to know what dy dt is. I know that. And I need to know what theta is. So theta is changing, but I need to know what theta is at this instant. So that's why I had to set up this triangle over here. Because at this instant, what is theta? So let's switch colors and do that in red. So let's figure out what our angle is. So to figure that out, we would say tangent of theta is opposite over adjacent. So tangent of theta is 5/30. So theta would be the inverse tangent of 5/30. And we can figure that out on our calculators. The inverse tangent of 5 divided by 30 would be 0.165148 radians. We're going to need that here. So I can plug it in now, or I can wait until I've solved for d theta dt. So let's go back to blue. All right, so to get d theta dt by itself, I either need to divide both sides by secant squared, or I can multiply both sides by cosine squared. I like to think about it that way. So if we go back to the step before this, if I multiply both sides by cosine squared of theta, and that color is kind of hard to show up, so I'll switch. So off on the side, if I do cosine squared theta times secant squared of theta, secant squared of theta is really 1 divided by cosine squared of theta. So cosine squared times secant squared is going to cancel out. So when I multiply both sides by cosine squared, the cosine squared and the secant squared cancel out, which is how I get the cosine squared on this side. If you would rather write it as 1/30 dy dt divided by secant squared of theta, this is equivalent to that, so you'll get the same answer. All right, so back to blue. Let's finish this problem out. D theta dt would be 1/30 times cosine squared. At this instant, the angle is 0.165148 radians, and then dy dt was 3. Now, d theta dt, when we get our answer, we need to have units. Theta would be radians, time would be seconds on this problem. So when I multiply everything out on my calculator, I would get 0.09729 radians per second. That's my answer. I always like to write my answer as a sentence. So I would say the angle of elevation is changing at 0.097 radians per second. So on a lot of these problems, you're going to have to think about the picture twice. Once while it's changing, and then once at the instant that you're looking at. Because a lot of times you'll need to find one of the values by looking at that instant. But then you need to think about the overall picture when the variables are still changing. This is the one you want to use when you're doing your calculus and you actually take the derivative. Hope this helped. Feel free to email your instructor if you have questions. Thank you.